Okay, so now we're going to talk about this new class of integrals we're going to learn to actually do, which are trigonomic integrals. So this is section 7.2. And the best way for me to try and explain this is to just do a few examples, and then we'll see how it works. We'll see what strategy we're invoking in these cases. So let's start with the following problem. This is example 1, I think. Let's integrate cosine to the power 3 of x dx. So, what can we do with this? Well, first let's note that none of our techniques help. We can't do any u sub, there's no integration by parts. So we have to, there's no immediate u sub. We have to do some kind of thing to make this into an easier form. And what do we know? So, we know we have this trig identity, sine squared of x plus cosine squared of x is equal to 1. Yeah? So what we can do is if we let this thing be star, then we can write star is equal to what happens when we take out one of the powers of cosine, and let's write cosine of x as 1 minus sine squared of x. Okay? And then we're going to have 1 minus sine squared of x cosine of x dx, like this. Yeah? And now this is something we can actually do something with, because if we look at this for a little bit, integration by parts isn't going to help, but u sub actually will, because if we let u be sine of x, then du by dx is cosine of x, yeah? And therefore we have that du is equal to cosine of x dx, which is this structure right here, right? Cosine of x dx. So then we can turn this entire integral into something to do with u. So star is equal to the integral of 1 minus u squared du. Yeah? So now that's easy. It's just a polynomial. So then this is just equal to u minus u to the 1 over 3 plus constant c. And then we put things back in terms of x, which is what we want. So we have sine of x minus sine to the power 3 of x over 3 plus c, and there we go. Yeah? So, with a little bit of manipulation, just changing things around with the identity, we can actually do it. Let's do a different example. Now, what about this? This is example 2. Now we're going to have sine to the power 5 of x and cosine squared of x dx. Okay. Look at this for a second. Do you have any suggestions of how we're going to handle this? Do a sub with u is equal to cosine of x, then use this identity. Let's call this thing star star. What happens? So if we're trying to do a u sub with cosine, we want to turn as much of this as possible into cosine and just have one sign at the end. Yeah. So let's write this as sine to the power 4 of x, cosine squared of x, and let's put 1 sine of x right here, dx. Yeah. And then this identity here also gives us that sine squared is 1 minus cosine squared. That's already been suggested to us, right? Yeah. So, and we know that sine squared of x is 1 minus cosine squared of x. Yeah? And then we can use that to replace this cosine to the power of 4 with 1 minus cosine squared squared. Yeah? And if we do that, what happens? We have 1 minus cosine squared squared, cosine squared of x, sine of x dx. Yeah? Everybody with me? Give me a thumbs up if this is making sense. Show me if it's not making sense. Give me a thumbs down if it's not. Okay, everybody's good. And then now we're in a good position because with this u sub right here, right? So we know that du by dx is equal to minus sine of x dx, right? So we have this structure over here is over here, yeah? So then we can turn everything in this integral into something to do with u, yeah? And then we're okay, because it's just going to be integrating a polynomial in u. Yeah? So let me see if I can erase the top of the board so I can keep all the information right here. Because we're differentiating cosine itself, right? Where is our u? Here is our sub here. So we differentiate cosine, we have negative sine. Differentiate sine, we have cosine. No? Thank you for the question. So with this board, I have either the choice to completely erase it with this kind of window cleaner or to do this painful process of like trying to scrub a bit of it out. So sorry for this slow thing I have to do here. This is called a light board. So it's it works by, it has these lights around the edges which shine light through the sides of the glass, and it's a particular kind of glass, very fancy glass, so that the light is trapped, and the only way that it's like very pure glass, and the light is trapped, and the light can only escape by flowing out through the ink that I put onto the board. It's like some invention of some engineer, I think in Michigan a couple of years ago, and I bought one and put it in my home because of doing this kind of stuff. So yeah, Google Lightboard if you but these are expensive toys, so all right, so we are here. Now let's call this thing star star star, and then star star star. We're going to turn everything in terms of u, right? So we're going to have integral of 1 minus u squared, and this thing we've learned, oops, this makes no sense what I just wrote here. Should be this. This thing, the u, is minus sine of x dx. Yeah? So this thing is now going to replace by minus du, but we're going to put the minus sign right here. I just multiply this thing through, integral, and then we have 1 minus 2 u squared plus u to the 4 u squared du, and then we multiply it through, and so we're going to have the integral of u squared minus 2 u to the 4 plus u to the 6 du. I'm going to have to write small because I'm running out of space, and then this is going to be u to the 3 over 3 minus 2 u to the 5 over 5 plus u to the 7 over 7 plus constant c, and then we put that back in x form using our sub here, which was the cosine, right? So we have cosine of x to the 3 over 3 minus 2 over 5 cosine x to the 5. The rest of it down here. So we have this term, plus cosine of x to the 7 over 7 plus constant c. And that thing is our answer. Everybody happy? Yeah? Thumbs up. Go ahead. Yeah, I just made a mistake, that's why. So I think I dropped the negative sign. There we go. So we have a negative sign from here. So this is negative, this is positive, this is negative. And therefore this is negative, positive, negative. Okay. All right, now we're good. Thank you for these questions. Everybody happy? All right, so let's talk about the strategy. What did we do? We saw this expression right here. We have two games. We have two things we can possibly do. We either are going to do a u sub with cosine, or we're going to u sub with sine. Right? If we do a u sub with cosine, then we're going to have to turn as much of this expression as possible into cosine and try and have one sine left at the end. So it's going to be all cosines and then sine dx. Yeah? But we can't do that because if we get rid of this thing, the only thing we can replace it with is, from this trig identity, it's going to be 1 minus sine squared. So we'll have the entire thing in terms of sines, and then we know cosine at the end, right? So doing a u sub with u is sine isn't going to work. So the only other choice is u with cosine. And if we do u with cosine, we're going to try and turn as much of this as possible into cosine, but we need one sine left at the end. Yeah? But that we can actually do, because when we break this up like this, sine to the power 4, cosine squared sine dx, this thing we can turn into cosine. Which is what we did right here. And now we're in the position to do a u sub because we can turn all of the cosines here to the left of this line into u, and then this thing just becomes minus du. All right, everybody happy? Well, actually let's do a very different kind of guy. Let's consider this guy, example 3. If we do something like this. Okay, so the strategy that we've kind of figured out is that if we can turn the entire expression to a bunch of cosines and then just one sine left, then we can do a u sub with u as cosine, or conversely, a bunch of sines with one cosine left, we can do a u sub with u as sine. Nothing like that's going to work here, right? Because we just have sine squared. So we have to have a different tool. And indeed, we do have a different tool. And these are these double angle formulas for trig. So these are some identities which you've no doubt seen before. So we have cosine squared of x equals 1 over 2, 1 plus cosine 2x, and sine squared of x is 1 over 2, 1 plus right? So with these guys, we can actually get to work on this thing, which has an even power, just because we can turn this thing into this thing right here. So let's call this thing star. And then star is going to become integral from 0 to pi of 1 over 2, 1 minus, cosine of 2x dx. Yeah? So what are we going to do with this? This thing is now something we can understand, right? Because let's take out this 1 over 2. The antiderivative of 1, that's easy, right? It's just x. And then we ask ourselves, what's the antiderivative of cosine? Or cosine 2x. And that too we can figure out, right? Because it's just going to be, if we just try and do sine of 2x and we differentiate it, it'll give us cosine of 2x with a factor of 2, right? So we just divide by that, and it's going to give us what we want. So this thing will be x minus sine of 2x over 2. Yeah? And then it's easy, right? Then we just plug in these numbers. And then when we plug in x is pi, we get pi. Plug in x is pi into this, we get 0. Yeah? And then x is 0 into this, we get 0 as well. So what do you get? We get 1 over 2 pi minus 0, which is pi over 2. Everybody with me here? Good. Thank you for the question. All right. So when we have something like this, we're all good. Let's do this thing. Example 4. Suppose we have this integral. So this is not a definite, it's an indefinite integral. What about this? What do you suggest we do with this? I should be writing bigger. Okay, I'll write bigger. Perfect. Yeah, if we write this as 2 sine squared, so sine to the power 4 is sine squared times sine squared, so then this thing is equal to the integral of sine squared of x times sine squared of x dx, right? And for sine squared, we have this identity, which we used before, right? So that's the integral. Let's pull out this 1 over 4 over here. And what do we have? We have 1 minus cosine of 2x, 1 minus cosine of 2x dx. Yep. Let's multiply that through. So we have 1 over 4. And we're going to have 1 minus 2 cosine of 2x plus cosine of 2x squared dx. Yep. Cool. All right. So now what from this stage? What can we do now? Can we just write the antiderivative of this thing, or do we have to think some more? Yeah, I see what you're saying. The cosine squared so cosine squared for sure is a problem. We can find the antiderivative of this thing just the way we did before, and for this thing. However, if we turn this into 1 minus sine squared 2x, then we're going to have to integrate this sine squared, which is actually something we've already done, right? This is almost, yeah, it's something we've already done, yeah? Using this half angle formula, yeah? But we could also just directly use this half angle formula, this one, on this guy right here, yeah? And then would be able to turn it into something we can actually integrate. So the problem is just this guy, but we can use this thing, which we have, to do it in the same way we did before. Yeah? So we have another identity to apply to this expression before we can do it. So let's do that. 1 minus 2 cosine 2x. And then we're using this identity over here. So it's going to be 1 over 4. Oops, sorry, 1 over 2. 1 plus cosine. And now it's going to be 4x, right? Because this is cosine 2x squared, but we're putting it into this. So the 2x now becomes 4x. Yeah? So we have 4x right here. And now this is all stuff that we can actually integrate. Yeah? This is all stuff we can actually figure out. Yeah? So that's what we're going to do. We'll write this guy out and integrate the entire expression. So let's see what we get. So then this is 1 over 4. What constant term, well, let's try and do this. No, let's do this more than one step. So what constant term do we have? We have 1 plus a half, so we have 3 over 2. This thing remains the same, so it's going to be minus 2 cosine 2x dx. And then this thing is going to be plus a half cosine of 4x dx, yeah? And then, actually, now let's just put the antiderivative in. What happens? So the antiderivative here is going to be 3 2x. We ask ourselves, what do we differentiate to get this thing? Well, if we try with just sine of 2x, then we're going to have exactly what we want, right? This is going to differentiate sine of 2x. It's going to be cosine of 2x times 2, which is exactly this thing. Yeah? So then this thing is sine of 2x. And then what about here? Well, if we try with sine of 4x and we differentiate that, we're going to have minus cosine of 4x times 4, which is not quite what we want. So let's put a minus 1 over 8 here, I guess. And then we're going to have sine of 4x. And what happens when we differentiate that? We're going to get cosine 4x is 4. So then, well, minus cosine, oops, not minus, this is positive. So we differentiate this thing. We do indeed get this thing. And I got the wrong sign here as well. This is a very confused day for me. All right. If we differentiate this thing, we get this thing. If we differentiate this thing, we get this thing. If we differentiate this thing, we get this thing. Okay, that should be the right thing. And indeed, it is. Oh, plus constant c. 3 over 2 came from this here, plus a half. Yeah? Are you good with that? Cool. Any other questions? Good. Thank you for the question. Any other questions? All right. Give me a thumbs up if everybody's with me here. All right. Good. So what was our strategy? We saw cosine to the power of 4. We know that we're not going to have a chance to do this u sub type method, which means putting a whole bunch of sines and then one cosine, or a whole bunch of cosines and one sine. The only thing we have a chance to do is to reduce it down using these formulas right here. But we have to do it in 2 steps this time. We do it to 1 step. We still have 1 cosine squared type power left. Do it another time. We get back to here. And then it's all good. It's all sorted out. Yeah? Cool. All right. So from this, we are in a position to develop a general strategy for sines and cosines. Okay, general strategy. So we're going to integrate sine to the power m of x, cosine to the power n of x dx. Okay? All right. Can you see it? Is it back now? Yeah, I'm having the same experience that some of that my whole screen of faces will just cut out for a second and then come back. I don't know what to say. I pay for fancy broadband, so where the blame is, I don't know. But if I stop for more than 5 seconds, then definitely tell me. All right. Everybody can see this now. Everybody's good. This is our question. We want to find a general strategy. Yeah. Well, we want this. Yeah. I will try and do bigger exponents. Unfortunately, m and n look quite similar, right? All right. So, think about what we've done. What do we do? What cases can we consider? So let's consider this case. Suppose m is odd. Yeah? If m is odd, so m is equal to 2k plus 1 for some k. Right? That's what being odd is. Yeah? How would we solve this problem if m was odd? And remember, our identity is sine squared of x plus cosine squared of x is equal to 1. Yeah? How do we solve this identity? How do we solve this integral, I should say? Yeah. So in that case, let's write it like this. So we're going to have sine of 2k of x cosine n of x, and then one of these signs are left. Like this. Yeah? Someone else, tell me why that's good. Why is that a good move to do? For the cosine. And in order to do that, we have to turn everything from that side into cosines. Yeah? So that when we do u is cosine, we're going to have du by dx is minus sine, right? So then we're going to have minus du is sine x dx. Yeah? So we need to turn everything to the left here. I don't know if it's your left or not. Probably it's not. We have to turn everything on this side into cosines. Yeah? But we can do this because this is an even power. Yeah? This is an even power, and we have this identity. So you know what sine squared is 1 minus cosine squared. So we can rewrite this like this. So then this thing is going to be 1 minus cosine squared of x to the power k cosine to the n of x. And then here we have sine of x dx. Yeah? And now we can do this u sub. We can do u is cosine of x. Yeah? Therefore, du by dx is minus sine of x. Therefore, minus du is sine of x dx. And we're in good shape, right? Because then this entire expression becomes integral of 1 minus u squared to the k, and then this thing will be u to the n, and now we're going to put a minus sign in front because it's minus du is this thing, so then we just have du, and this is just a polynomial in u, and we can integrate it, right? Give me a thumbs up if you are happy with this. Cool. Yeah? So this case we can do, yeah? So long as we have this is odd, we need also, no, that's all we need. We just need this is odd. That's all we need. M is odd and we're all set. Yeah? Cool. So that's one case. Let's do another case. So let's call that case 1. Case 2. Suppose that n is odd. Let's just write this like this. N is equal to 2k plus 1. Let's suppose that. Yeah? Okay, so if that's the case, what's your suggestions then? So if that's the case, then this expression star is what? It's going to be sine to the m of x cosine to the 2k plus 1 of x dx. What are we going to try and do then? Yeah, let's pull out one of the cosines. Yeah? Do that, and we have this thing, sine to the m of x cosine to the 2k of x cosine of x dx. Yeah? And we can do the same thing. We can turn this stuff into a bunch of signs using this identity over here, right? So then this thing is sine to the m of x 1 minus sine squared of x to the k like this, yeah? And then this thing remains the same. And now what's the u sub that we're going to do at this point? U will be equal to what? Someone who hasn't answered yet. Yeah, if we let u be sine, then all this stuff here on that side turns into a bunch of u's, and this thing will just become just the u itself. Yeah? Cool. So if either of these numbers is odd, we can do it, right? So if m is odd, we can do it. If n is odd, we can do it. And we're all set. Yeah? Yeah? So the only remaining case is where m and n are even. Okay? So when m and n are even, that's our last case. Yeah? All right, I'm going to erase the board. You guys think about how we're going to deal with that case. We have m and n are even. So we're going to have the integral of cosine to say 2k of x, and then sine of say 2r of x. How did we handle this before? We had these identities, right? We had cosine squared of x is equal to 1 over 2, 1 plus cosine 2x. Yeah, and we have sine squared of x is 1 over 2, 1 minus cosine 2x. Yeah? So what do we do in this case here? Yeah, we can use these identities to replace this by this, or this, and this by this, yeah? And if we're lucky, then one of those things might turn out to be odd, yeah? Or it could be that they're both still even, right? So if we have an even number and divided by 2, it doesn't have to be odd, right? If we have 8 divided by 2, it's 4, it's still not odd, yeah? So we might have to do it again, yeah? We might have to do it again, yeah? But these things give us the ability to bring down these even powers. We divide them by a half, yeah? And this is much more painful than the other procedure. So in the other procedure, it didn't matter how big these numbers were. If 2k plus 1 was 1,000,000 or 1,000,001, then that was still fine. The u sub method just does it very easily, right? In this case, every time we reduce the powers by a half, we have to put in these identities, multiply through. It's a big pain, yeah? But we can still do it. So those couple examples we did with even powers, when we just had an even power just on one of these things, you know, I think sine or cosine, well, obviously, I think it was sine the first example. I can't remember if it was sine or cosine the second one. But we just did this procedure, right? And the most complicated example we had, we just actually did it twice, right? So this gives you a kind of hint of how this goes, that in practice, when you see these problems and you just have even powers, you're not going to have very high even powers because it's just going to take you too long. It's going to be too complicated a question. So if there are even powers here, at most I would expect it to be power 4. Yeah, I wouldn't expect it to be more than power 4. Maybe power 6, you'll find some examples. But you're not going to have to do this procedure of substituting in these identities more than a couple of times. Yeah? So that means that we can do any integral of the form cosine to the m of x, sine to the n of x, dx for any m and n. Yeah? So when you see an integral like this, you should feel confident that we can do it, right? Because either one of these numbers will be odd, yeah, And if, say, this one is odd, then we're going to pull off one power and turn everything else into sine and do a u sub with sine. Or if this guy here is odd, we're going to pull off one power of sine, turn everything else into cosine and do a u sub with cosine. Yeah? Or they're both even and we reduce it with this thing. Yeah? Cool. So these things, which maybe look like difficult integrals, actually not. Yeah? Because we have a method to do it. And the algorithm to do it is kind of common sense, if you understand it, right? It's just common sense. Yeah? So when I wrote it all out, it was kind of lengthy, but I just summarized it there in like, whatever, 20 seconds. Either this guy is odd, we pull out one power, turn everything into sine. Either that guy is odd, pull out one power, turn everything into cosine. Or they're both even and we do this. Huh? So this is not a difficult thing, ultimately. Okay, you practice this, you'll be fine with it. Everybody clear on this kind of stuff? Everybody feel happy? Any questions on this? Yeah, if both are odd, you can choose your favorite function, sine or cosine, to do the sub with. I think I prefer sine because when I differentiate it, it doesn't change. Sine goes to cosine without a minus sign. So, yeah, if they're both odd, then you're in good shape. Yeah, cool. How much time do I have left? What time is it now? 11:07. So actually, no time. So this is a perfect time to start. Okay, so next class we're going to learn how to do a similar thing, trig subs, when we do sec and tan, and it'll be a similar story. We're going to search for the correct u sub using what we know about differentiating sec and tan and the identities. You're already in a position to practice this stuff here, so a good idea would be to do the practice questions where you do the sines and the cosines. Make sure you've understood it because it will help you for this thing we're going to learn on Thursday, on Friday, which is a bit more complicated. Okay, cool. I have office hour exactly now, so if you have questions, stick around, ask me. Otherwise, I'll see you all on Friday. Have a good day. Bye-bye.